Hello again. Remember the gravitational force equation we showed in an earlier video? We'll now use it and basic physics to derive the equation of motion for spacecraft. You should now see the equation on my right. Recall that r is the distance from the satellite to the center of Earth. Uppercase m is Earth's mass, lowercase m is the satellite's mass, and g is the universal gravitation constant. Force is mass multiplied by acceleration. Therefore, we can also write this equation as shown, where r represents the satellite's position relative to the center of Earth, and the double dot over the r represents the satellite's acceleration. Remember that velocity is position's rate of change versus time, and acceleration is velocity's rate of change versus time. If you understand calculus, you should recognize the previous equation as a simple second-order differential equation. It is the equation of motion for a satellite outside the atmosphere when only Earth's gravitational acceleration is considered. I now show the equation of motion in vector format. Vector format means that the distance, velocity, and acceleration are broken down into the three ECI coordinate system axes. This format is indicated by the arrow over the r. Note that the negative sign indicates that the acceleration vector is in the opposite direction of the position vector. For example, the position vector points in a direction from the center of Earth to the spacecraft, while the gravity acceleration vector points from the spacecraft to the center of Earth. This equation is equivalent to the mathematical flowchart you now see on my right, where the symbol in the two boxes represents integration, the repeated summation over time. Remember from calculus that the integral of acceleration relative to time is velocity, r, with a single dot over it, and the integral of velocity relative to time is position, r. This satellite equation of motion can be solved iteratively on a computer where each software loop represents one step in time. I show the computer flowchart in the next image. Note that I did not include centrifugal force in the spacecraft's equation of motion. I only included the forces due to gravity. That's because forces due to gravity are currently the only external forces applied to the spacecraft. Centrifugal force is not a true force. It is the result of inertia and is a reaction to the change in direction caused by other forces such as gravity. It's inherent in the mathematics of integration when solving the equation of motion. Now I show you how to include the acceleration perturbations due to such things as rocket forces, Earth's bulge, solar pressure, the moon's gravity, the sun's gravity, and upper atmospheric drag in this equation of motion. Note that all perturbations are converted to acceleration before adding them to the acceleration due to Earth gravity at the satellite's current position. If you are an advanced student of orbital mechanics, you may be wondering how we know where the moon and sun are without solving the four-body equation of motion. We know where these bodies are relative to Earth using published equations that are highly accurate for plus or minus 100 years. And since we assume the spacecraft's gravity has negligible effect on Earth, Moon, and Sun, we can greatly simplify the four-body problem to a one-body equation of motion in Earth's gravity field with perturbations from all other forces. We plan to produce more videos in the future, so subscribe to this channel if you want to see more videos describing space flight and orbital mechanics. We also need your feedback, so please leave comments and like the videos you find useful. Goodbye.